In this lecture, we are going to do the buckling analysis of columns with different end condition. So till now, we have dealt only with column under pin-pin condition. The condition of pin-pin boundaries were consciously chosen so as to keep the derivation simple and to focus more on the concepts of instability and buckling. Okay, so now with an assumption that we have understood the concepts of instability and buckling well, we will move into a more generic case where the column can have any end condition. It could be fixed, it could be free, it could be hinged or pinned. Okay, so this particular example that we have considered is that of a fixed free column end. Okay, so this is a fixed free column, kind of a cantilever condition, fixed free column. Right, so the deformation under, so an axial compressive load P is acting at the free end. At the fixed end, of course, there would be a reaction force which will also be P and also will be axial and compressive. Now on the left hand side, I have shown how the column will be bent on application of the load, axial load P, or the left hand, this figure shows the buckled or deformed configuration, deformed or buckled configuration, okay, deformed or buckled configuration. Okay, so now let us try to derive the equation of motion, or sorry, let us try to derive the differential equation for this condition. Okay, so to do that, first let me draw the free body diagram of the problem. So let me take an elemental portion of the column. Okay, and let me draw the axis as well. So this is the Z axis. So this is the X axis, sorry, Y axis. This portion is dz. Okay, so so the forces that are acting are axial P as well as P. Okay, so there is going to be a moment M. Here there is a moment which is M plus dm by dz into dz. Okay, plus there would be a shear force Q. Q is the shear force. Okay, and likewise I have Q plus dq by dz to dz. Okay, so and of course Vz is the deformation at any z. So this is Vz. So this is going to be my Vz. Okay, so let us, even for just to make it more generic, let us also assume that an externally applied transverse force Q is acting on the column, just for the sake of generality of the derivation, and later we will say that Q is 0. Okay, so Q per length is acting on the column. Okay, now so this is my free body diagram. Let me now try to derive the equilibrium equation for the problem. So first let me do force balance in y direction. Force balance or force equilibrium in y direction. Okay, so let us see what are the forces in y direction. So one is going to be q plus dq by dz into dz minus q, okay, plus q into dz. Okay, that's all. That's all the force that I have in y direction, and for equilibrium this is going to be 0. So now if I simplify this, I'm just going to have dq by dz plus q is equal to 0. Okay, so this is one important equation, and let me call this as equation 1. Okay, so now let me write down the moment balance equation. Now if I write down the moment about this point, so I'm going to find out the moment about this point. If I do so, then the moment there is going to be m plus dm by dz into dz minus m plus q plus now let us see what is going to happen to the axial force. So P into dv by dz into dz. Okay, right? So dv is so dv is going to be this thing. So it is going to be dv by dz into dz, and that should be equal to 0. Okay, so now out of this entire derivation, I can make certain term almost equal to 0. So this term has dz square, so this term can be neglected as it is going to be too small. Similarly, this term can also be neglected, right? Because they have dz square, which is going to be a very small term. Okay, now if I simplify this whole equation, I am going to get dm by dz plus q plus p dv by dz is going to be equal to 0. So this is my second equation. Okay, now I can use my equation 1 into equation 2, but to do that I have to take another derivative with respect to dz, and that is going to give me d2m by dz square plus dq by dz plus p d2v by dz square is equal to 0. Now this one is going to be equal to minus q, and that could be written as 0 if there is no transverse force. Okay, So if there is no externally applied transverse force, then Q is equal to 0, and therefore dQ by dZ is eliminated from the equation. So therefore the equation gets much more simplified, and I have d2m by dz square plus p d2v by dz square is equal to 0. Okay, so this is my third equation. Now m is nothing but, I know, right, m is nothing but ei into d2v by dz square. Okay, where b is the transverse deformation. So therefore this equation can be written as d2 by dz square into ei d2v by dz square plus p d2v by dz square is equal to 0. Okay. Now if I assume that the column has a uniform cross section, that is ei is not varying with z, then this expression can be further simplified and written as d4v by dz4 plus p d2v by dz square is going to be 0. So this is the governing equation, because this entire equation is now in terms of v, which is the transverse deformation or the buckling deformation. Therefore this is the governing differential equation of buckling. Okay, so this is going to be my governing differential equation. So for a pin-pin case, okay, we have seen that it was ei d2v by dz square plus p into d2v by dz square. But here we have the fourth order equation. Okay. Now if this is the equation, we can very easily find out the generalized solution for this equation. So the generalized solution for equation four is going to be Vz, that is going to be A plus Bz plus C cos mu z plus D sin mu z. Okay, so this is going to be the generalized solution. Now on this equation, let me call this as equation 5. So now on this equation, I will apply the boundary conditions. So let me write down the boundary conditions for a fixed free column. Okay, so what are going to be the boundary conditions? So at the fixed end, that is at z equals to 0, so at the fixed end, which is z equals to 0, my boundary conditions are Vz is equal to 0 and the slope, that is dv by dz at z equals to 0 is equal to 0. Okay, and at the free end, which is at z equals to L, I have the moment is going to be equal to 0 and the total shear force is going to be equal to 0. Okay, So if I try to write the moment in terms of the deformation V, then the moment is going to be, this is going to give me EI d2V by dz square at z equals to L is going to be 0. Now what is going to be Q? The Q is going to come from equation 2, where Q is going to be minus dm by dx minus p dv by dx, right? This is going to come from equation 2, right? Let me just go back to equation 2. So from this equation, I get Q for a column with axial compressive load P is going to be minus dm by dz minus p dv by dz. Okay, so therefore this whole thing can be written in terms of displacement, which is minus EI d3v by dz cube. Sorry for this x thing. This is are all dz. Okay, so this is dz. This is dz. d3 by dz cube minus p dv by dz. And that is equal to 0, right? So these are the 4 sets of boundary conditions that I have. So by using this 4 boundary condition, I can evaluate the constant A, B, C and D. Okay, so let us try to do that. Let us try to evaluate the constants A, B, C and D. So from V0 equals to 0, we are going to get A plus C is equal to 0. Let me call this as equation A, right? So now from dV by dz at z equals to 0 is going to give me dV by dz at z equal to 0 is going to give me B plus mu D is going to be equal to 0, right? So that is going to give me this second equation. So that is, let me call this as equation B. Now comes the boundary condition that EI, that is d2v by dz square at z equals to L is equal to 0. Okay, and that is going to give me C plus D is equal to 0. Sorry, C cos mu L plus D sin mu L is going to be equal to 0. So that let me call as equation C. Now, so EI d3v by dz cube plus p dv by dz equals to 0 implies d3v by dz cube plus mu square dv by dz is equal to 0 at z equals to L. And if I write that down, what am I going to get? What is d3v by dz cube? So d3v by dz cube is going to be minus mu cube into C sin mu L, okay, and then I have no, this is going to be cos, and then I have minus cos square, and this is going to be plus. Okay, and then I have minus mu q c, sorry, d cos mu l plus mu square dv by dz is going to give me b, okay, minus mu c sin mu l, okay, plus mu d cos mu l, okay, and that is going to be equal to 0. Okay, so out of this, this perhaps get cancelled with this get cancels with this, so what is left with me is mu square b is going to be equal to 0. So out of which mu square cannot be equal to 0, therefore I have b equals to 0. So this is my equation D. Now if B is equal to 0, of course my D is going to be equal to 0. So B and D is going to 0, therefore my Vz ends up being A. In place of C I have minus A cos mu Z. Am I correct? So let me just check. So it is going to be C cos mu Z. Okay. So that is the final expression for Vz that I have. Now let us see what is A going to be. Okay, so if my B and D is 0, I even don't need this at this point. Okay, so D is equal to 0. Therefore, from equation C, we get C cos mu L is equal to 0. And C cannot be equal to 0 for non-trivial solution. Therefore, cos mu L has to be equal to 0. And that is possible when mu L is going to be 2n minus 1 pi by 2, or mu is going to be 2n minus 1 pi by 2l. Okay, so let me just summarize what we have done. So we have seen that for a fixed free column, fixed free perfect column, Vz is going to be some constant A, 1 minus cos mu z, and mu is going to be 2n minus 1 pi by 2l, which implies that mu square is equal to P by EI is going to be 2n minus 1 pi by 4l square. Okay, so from there I can say P critical is going to be 2n minus 1 whole square pi square by 4l square into EI. Okay. Right? So similar to what we have done for a pin-pin perfect column, here also we can see that the fixed free column is going to be in stable equilibrium under the action of an axial compressive load P, when P is going to be the odd multiple of pi square by 4l square into EI. Okay, therefore this value of P is going to be the P critical or the critical buckling load, and the deformation of the column at the neutral equilibrium when P is equal to P critical is going to given by P Bz, which is going to be some arbitrary constant which can take any value into 1 minus cos mu z. So the nature of the solution that we have got is similar to the nature of the solution that we had got for the pin-pin column and pin-pin perfect column. So even here, similar to that case, this is an eigen solution and the deformation is the eigenfunction, whereas the P critical value that we obtain is the eigenvalue of the solution. Now we can see that the first critical load or the first critical buckling load, so the first critical buckling load is going to be pi square EI by 4L square. Okay, the second critical buckling load is going to be 9 okay. Similarly, the deformed shape is going to be an arbitrary constant A into 1 minus cos pi EI by 2L. Okay, and similarly here it is going to be so this is P critical 1 and this is going to be P critical 2 and so on. We can also find out P critical 3, P critical 4, etc. Okay, so now we have derived a procedure by which we can find out the critical buckling load for any column, with any perfect column with any end condition. With using the same methodology, you can find out the critical buckling load and the buckling analysis for a fixed column and so on. Okay, the one concept that I should talk about next is the concept of effective length. Okay. So let me talk about effective length.